Hi, everybody, and welcome to another installment of One Dimensional Motion with Miss Palachek. I am hoping that by the end of this video, you will have a better understanding of our motion graphs, and you will also have a better understanding of kinematic equations. So we're going to jump in right away, and we're going to go back to something we talked about yesterday. Yesterday, we talked about graphing position versus time graphs, and this is actually the same exact graph that we used, but we have y equals mx plus b. Okay, y equals mx plus b for any of our graphs are linear graphs. And so from this, we can pull out that our slope in this case is going to be our change in position over change in time. Okay, here's our change in time. Okay, here's our change in position. Okay, and when I find my change in position over change in time, I'm able to get my velocity. Okay, now if I have a positive slope or a negative slope in velocity, that shows us our direction. Okay, and then also if I have a steep slope, it means I'm going fast. And if I have a shallow slope, it means that I'm going pretty slow. Okay. So when I'm looking at this graph right here, this graph is a little bit different than the stuff that we looked at yesterday, but hopefully you saw something like this in your moving man activity. And you're thinking to yourself, oh my gosh, my slope is not constant here. My slope is changing. Yes, that is true. If velocity is, or if your slope is changing, velocity is changing. So right here, I have a slope here, my slope there. I'm taking the slope of my tangent line. Okay, the slope of my tangent line. So that slope is changing, especially like right here. Okay, so our slope is changing, so our velocity is changing. We have some kind of acceleration. So in section A, my object is starting rest and is starting from south of the home base and is moving towards home, increasing the speed gradually because the slope is increasing. Then my object passes home and gradually slows to a stop, still moving in the north direction, turns around and gradually speeds back up again, heading south. Then in section D, I'm continuing, or my object is continuing to head south, gradually slowing to a stop. Okay, so when we look at that, what does everything look like? Because in AP Physics, you're going to be asked to graph all of this motion. So in order to do that, we need to be able to go from our position versus time graph to our velocity versus time graph to our acceleration versus time graph. And if you're looking at this and thinking, oh my gosh, there's no way that I can do this, just know that that's where everyone starts, and that's okay. Okay. But what I'm doing here is I'm showing I'm showing that my velocity is changing. My velocity is actually increasing. And then I have my velocity. So this is caved down, or my slope is getting smaller. So my velocity is then decreasing. Okay. And then my velocity is increasing, but in the negative direction because you're moving back towards home. You're moving left in this case. So in the negative direction, so you're basically going from like 0 to -1 to -2 to -3 and whatever. So that's going to be increasing velocity still, okay, or increasing velocity at this point. And then you're going to be going back towards your 0. So you're going to be decreasing velocity, decreasing the velocity in that case. Okay. Now, in that case, you have your acceleration. Your acceleration is going to end up being positive because you have a positive slope here. And then it's going to be negative all the way here. So we have a negative value, and then we have a positive again. Okay. And that's because your velocity is decreasing in the negative direction. Okay. Now, something that I did not point out yesterday in our notes that is very, very important in AP is that what if I wanted to figure out the position that has been traveled through from a velocity versus time graph? If I wanted to do that, notice that my y value is velocity and my x value is time. When I multiply velocity times time together, I end up getting change in position. So the area under a velocity versus time graph is change in x. You guys, this is super important. You really need to remember this. So please make sure that you write it down in your notes, okay? So looking more at that graph a little bit, we're going to be looking at our slope, okay? So our slope, if the slope is positive, our velocity is positive. If the slope is negative, so here I have a negative slope, our velocity is negative. And if our slope is 0, like in this case, then I have a 0 velocity. Now, if the slope is steep, I'm moving fast. If it's gentle, I'm moving slow, or if it's shallow, I'm moving slow. And if it's flat, I am not moving. So I'm not changing my position. So, how do you know what's happening with your position? You know that your position is increasing or decreasing. Increasing means that you're moving forward. So, here I'm going from a negative value all the way to a higher positive value. So, if I'm increasing, I'm moving forward. If I'm decreasing, I'm moving backward. So, here I'm moving forward towards home and then forward to, we'll say, to the right. And then as I'm decreasing my x value, I'm moving backwards. Okay. So concavity, what does concavity mean? And what I mean by that is you'll see this goes up, okay? It caves up, so it's like forming a bowl or it's forming a U. If it concaves up, it means that there's positive acceleration. If it concaves down, that means that there's negative acceleration. So down has an N in it. So concave down means that it's negative acceleration. Concave up means it's positive acceleration. So here you have concave up again, you have positive acceleration. Okay, that's just looking at these graphs. That's just another way to remember how to determine your positives and your negatives. So let's take a look at some of these motion graphs and some of the notes for motion graphs. So in this question, it says an object moves in a manner as shown in the graph to the right. What does the slope mean in this type of graph? So the slope, whatever I can do, I can divide my y divided by my t. X divided by t gives you velocity. So the slope of this type of graph of my position versus time graph gives me velocity. Now tell me, is my slope positive or negative? Well, it's negative, negative, negative. So it is definitely negative. Is the slope constant, changing to become more positive or changing to become more negative? Well, changing to become more positive is kind of like changing to become less negative. So in this case, it's becoming less negative or less steep. So it's going to be changing for more positive. And describe the motion. So this object is, because the velocity is negative, we know that the object is moving left and it's becoming more negative. The velocity is getting is decreasing, so it's slowing down. Okay, so going to our next slide, our next question. Here we have question number 8. It says, an object moves in a manner as shown in the graph to the left. What does it mean that the graph values are below the x-axis? So remember, it being below the x-axis, our velocity is negative. So because we have a negative velocity means what? Negative velocity means that it's moving left or it's moving in the negative direction, okay? What does the slope mean in this type of graph? So the slope would be velocity divided by time, which is acceleration. Is the slope positive or negative in this case, or 0? It is definitely negative. Now, is it constant, changing to become more positive, or changing to become more negative? It is a constant slope. I would be able to figure out what that value is. So let's describe this motion. Because our velocity is negative, we have our object is moving left, okay? And it's actually speeding up. And the way I look at that is because I'm starting at 0. Then I'm going to -1, -2, -3. So the magnitude of my velocity is increasing. So in this case, I'm speeding up. So I love these types of questions because these types of questions really check to see if you understand what's going on with the motion and what's going on with the graphs, what they're explaining. So for example, in this very first one, I am seeing that my position is changing at a constant positive rate, okay? Constant positive rate, that means that I have a constant positive velocity. And so the only case is going to be right here. Now, in this case, I have my slope is getting significantly steeper. My slope is getting steeper, so I have an increasing velocity in the positive direction. That's going to be this right here. Now, in this case, my slope is getting less steep. So my velocity is decreasing, but I'm still in the positive quadrant, in the positive direction. So that's going to be right here. Okay. And then for my last one, I have a negative slope. I have a negative slope, which means I have a negative velocity, but it's constant. So therefore, it's this one right here. Okay. So looking at another question, this is where we start looking at things like instantaneous velocity. So in order to get the instantaneous velocity, we're going to be taking the slope of the tangent line. In this first question, it says an object moves according to the position versus time graph given below. Determine values for the following quantities about the object's motion, approximating as necessary. So what's the average velocity between t equals 0 and t equals 2? So when I'm looking at the average velocity, I just take my positions divided by my time. So my average velocity is change in position divided by change in time. My change in time is 2 minus 0. My change in position, it looks like that's 60 minus 0. So I'm looking at a 30 meter per second average velocity. Now the instantaneous velocity at 2 seconds. That right there, I'm going to have to figure out my tangent line, which I'm going to draw freehand right here, but I have it drawn in a graph. Okay, I have it drawn on a piece of paper here, and when I find the slope of that line, so I have to find the slope of my tangent line. Instantaneous velocity from a graph is the slope of the tangent, which in this case is going to be about 50 divided by about 2.75. And I did that by finding values on my line. Okay. And so I have 18 meters per second. And that makes sense because my average velocity is going to be higher because my slope is decreasing. So I'm slowing down. My velocity is getting smaller. And then right here, it says, at which time is it momentarily at rest? So at that point, it's going to be where you have a zero slope. Your zero slope is going to show up at about 4 seconds. Wherever your slope is 0, or basically you're changing directions. Okay. Okay, so this next question, this is our last graphing question for the day, and then we're going to do a couple of kinematics questions. So an object moves according to the speed versus time graph given to the right. Determine the values for the following. So we're looking at instantaneous acceleration. So we're looking at the instantaneous acceleration here, but I'm going to take the slope of this line because it looks like it's a pretty consistent line or a pretty constant line. So the slope of that line is going to be change in v divided by change in t. My change in t is 2 seconds, 2 minus 0. My change in v is 10 minus 0. So I end up getting 5 meters per second. Your instantaneous velocity can be the same as your constant velocity if you have a constant velocity, if you have a constant slope, okay? And then the next question is, what is the displacement? So the displacement is the area under the curve. So I'm going to figure out what this area is. And how do I figure out what the area is? So that's because this is change in x equals velocity times time. But because my velocity is changing and my time is changing, I find the area. The area of a triangle is 1/2 base times height, which is 1/2 times 2 times 10. That ends up giving me a displacement of 10 meters. Okay? So, kinematics equations. We use kinematics equations when we have a constant acceleration. And in this unit, we're using a constant acceleration. We're using a constant acceleration because we haven't talked about how to change the acceleration, how to go from 0 acceleration to a positive acceleration. So we have already derived this equation, okay? We derived that from our velocity versus time graph. We also actually derived our x final equals x initial plus velocity times time, okay? That's the same as it's going to be down here. Your x equals v average times time. Another equation for v average is v minus v initial divided by 2. I don't use that one very often though. And then the other two equations are equations that you could derive from a graph. And there are some physics programs that will graphically derive these equations. But you just need to know what they are and how to use them. So in this case, we have change in x equals v initial t plus 1/2 a t squared. And then here we have v squared equals v initial squared plus 2a times change in x. And we're going to use those a lot over the next couple of weeks. So let's look at a question. In 1865, Jules Verne proposed sending men to the moon by firing a space capsule from a 220-meter long, so I'm going to circle that. I know that that's going to be my change in position, cannon, where they would have exited the cannon traveling at 10.97 kilometers per second. So that's going to be my velocity final. So I have my change in x equals 220 meters. My velocity final is equal to 10.97 kilometers per second, which is the same as 10,970 meters per second. Okay. And then it says, what would have been the unrealistically large acceleration? So I'm trying to find the acceleration. Okay. And something else that I'm missing here is so experienced by the space travelers during the launch. So I can draw my picture. So in my cannon, I have my person being shot out of a rocket. They're going to go a distance of 220 meters. Okay. And when they exit that rocket, they're going to go 10,970 meters per second. Okay. So at this point, they started from rest. So V initial equals 0 meters per second. okay? So I'm trying to find acceleration if I have change in x, v final, v initial, and acceleration. So I'm going to actually go back, okay? I have change in x, v final, v initial, and my acceleration is my question, okay? So I want to make sure that I don't use an equation with time. So if I'm not using an equation with time, that takes out the first one and it takes out the second one. So the only other option I have here is this v squared equals v initial squared plus 2a change in x. So I'm going to use that equation, v squared equals v initial squared plus 2a times my change in x. Because my v initial squared is 0, I have v squared divided by 2 times change in x is equal to my acceleration. I always manipulate my equations first, manipulate my variables, and then I plug things in because I find that you make fewer mistakes that way. So in this case, I have 10,970 meters per second. Square that, divided by 2 times 220, which is going to end up giving me 440. And that's going to give me an insane acceleration of 274,000 meters per second squared. How would you like that? Like to be that person, man? Okay, that would be kind of crazy. So then taking a look at this next question, it says as certain arrow is accelerated. So we have an arrow, okay? And our bow and arrow right here, okay? And that's going to be accelerated by a bowstring at a rate of 42 meters per second. So acceleration is 42 meters per second squared. Assuming that it starts from rest, so starting from rest, again, very important, is 0 meters per second. Okay, starts from rest, we're going to circle that. How much time is needed? So I'm trying to find time for the arrow to travel through the first 15 centimeters. So 15 centimeters, I'm going to quickly convert that by dividing by 100. That gives me 0.15 meters. Okay. And so then also I'm looking for time. So I have A, V initial, X, and T. I do not have V final. So I cannot use an equation with V final. So this one is out. This one is looking pretty good. This one is out. So I'm going to have to use this one right here. Okay. So I'm going to go back to my question. I'm going to use my change in x equals v initial t plus 1/2 at squared. I'm going to start to manipulate my variables. This ends up becoming 0 because it starts from rest. I have my change in x equals 1/2 at squared. So then I end up getting 2 times change in x divided by a is equal to t squared, and I'm going to square root both of those sides. So I end up getting that t is equal to the square root of 2 times 0.15 divided by my acceleration, which is 42 meters per second squared. Okay, and I'm going to end up getting that my time it takes is 0.085 seconds. Okay, hopefully that was helpful for you. I know that these problems are going to take a while because they do. It just takes a long time just to get used to them. So keep your kinematics equations next to you. Use those, cross them out. If you have a whiteboard at home, use a whiteboard at home and reach out if you need some help.